For those of you who were with us at dinner last night, you'd have seen this gentleman stepping up onto the stage multiple times. So I'm not going to spend too long introducing him. He's completing his PhD at Bath, and this paper has come out of that PhD. So to introduce on integration of model-based systems engineering and simulation for evaluation of complex, quantitative, temporal key performance indicators. And this year's both best paper and best paper by a new author. Please welcome Lukas.
Right, good morning, everybody, and thank you for showing up to my presentation. So my name is Lukas Macha. Everybody just call me Lukas because it's just easier for the English to pronounce. And I'll be talking about a slightly controversial topic this morning, and that's essentially the integration of model-based systems engineering and simulation. And every time you do modeling, you have to have a purpose. So the purpose of our modeling efforts is the evaluation of complex, quantitative, and temporal key performance indicators. So here's just a quick agenda slide, so you know what's coming up. So I'll quickly introduce myself and the co-authors in a little bit more detail. And it seems to me that there's no presentation will be complete without talking about challenges and complexities in this conference. So I will quickly touch on that and talk about the challenges in automotive, and then get into the core of the paper, and that's on sort of using functional testing for evaluation, some of these KPIs and some of the difficulties with functional testing, and the importance of having KPIs that are quantifiable and traceable. And I will explain what I mean by KPIs as I go through the presentation, and then the last aspect of essentially migrating or transforming the information from SysML into simulation, and I'll close with some potential use cases that spun from this work. So there's a quick slide on the co-authors and myself. So I'm currently a PhD student, PhD researcher at Bath, and the topic of the PhD is essentially automation of verification validation activities from model-based systems engineering. So it's quite broad, but looking at sort of narrowing the scope as I move towards my final year. And I've got Julian Padget as one of my academic supervisors. He's a reader, which is like a senior academic position in computer science at Bath. And his background is in AI research. So he's got over 25 years of experience in research in artificial intelligence and agent-based modeling. I've got Peter Ebner from Austria. He's my industrial supervisor from AVL, which is my industrial sponsor. And he is in the role of chief engineer for model-based systems engineering and powertrain system functions. So he's got his background is automotive system development, and he's got over 20 years of experience in AVL itself. And then last but not least, Professor Chris Brace from Bath, who started off as an academic director of the CDT I'm part of. And then early this year, he took on the role of executive director of the Institute of Advanced Propulsion Systems Research, which is a new reform institute, which is a subsidiary of the University of Bath, and it's been set up at the Bristol and Bath Science Park. So maybe some of you have heard of that. And his main background is essentially automotive propulsion research. So he's got over 30 years of experience and from academia. Right. So talking about the challenges in automotive. And increasing complexity is usually the theme you hear here in the industry. And there's a big driver for shorter development cycles, right? So we've gone from 5 to 6 years down to maybe 2 or 3 years. So we need to get the products to market faster, and they are more complex. So this is definitely more challenging. Increase the number of functions, which might sound slightly counterintuitive because the interfaces have been simplified in vehicles. So if you sit in a modern car now, you won't have many knobs you can turn and many buttons you can press. So the interface to the user has been simplified. However, there's many more functions that need to be implemented to make that user interface simpler. And this is just sort of talking about the HMI. There's more complexities when it comes down to powertrain functions and things like advanced driver assistance systems. And most of the products are pretty much software defined now. And what I mean by software defined is that the hardware platform is common, and you the main definition for the products is within the software. So depending on how much you're willing to spend, how much money you're willing to spend, some of the attributes will be unlocked to you, some might not. So this would be maybe the maximum powertrain output you can get out of your vehicle. And we deal with continuous and discrete system dynamics, right? So these systems have been tested and verified in the past years, maybe in their own silos. So you would look at the mechanical parts and test those in separation from the software parts, how there's emergent behavior from interaction of the two that needs to be looked at, and this drives the complexity. And they operate in complex operating environments, and they're operated by users who haven't been trained to use those. And the cost of the integration, verification, validation is really increasing rapidly. And I've got one more slide on specifically just the IV&V approaches and costs. So functional testing seems to be the method of verification, at least what I've seen and what I pursue in my PhD research. And for that we use fairly broad landscape of different tool chains for different domains that you can see in automotive development. So we have things like thermal, mechanical, or control. They all use their own simulation tools. They all use their own methods. It's quite a broad landscape of the tools and simulation environments that you can come across. And depending on the means or the verification method that you specify for your requirement, you could be looking at combination of digital and physical models. So you have to make sure that those different environments work together in different stages of the system development process, and the number of artifacts will increases that you need for verification and integration. And what's often required is the interoperability and reuse between all of these artifacts, so that you can reuse them as you work through your development process, and you don't have to reinvent everything from scratch as you start a new stage. And so what's the trouble with functional testing? And here's a slide on just some difficulties with functional testing. I'm sure I won't be able to go through all of the difficulties with functional testing. But essentially they are scenario based, so we don't necessarily just test input in and output out, just slam the accelerator pedal and see what happens. So we try and put the systems through scenarios that the user would be putting the systems through, and try and evaluate the performance. Often there are competing objectives within different scenarios for different actors, for different end users. And we often define multiple targets or multiple KPIs for the system of interest. So I'll be going through this case study of a 3-lane constant speed adaptive cruise control. And we can see there are 3 KPIs set on here, which is one for maximum delta target speed, then mean absolute delta target speed, and then the disturbance on the longitudinal acceleration. And they all have quantitative measures, right? So we can't just say, well, the system passed or failed our test. We need to be able to quantify the system performance. And we ascertain the KPIs on emergent system behavior. So this is something that might be obvious to people working in the automotive industry. It's really quite challenging because the vehicle velocity cannot be attributed to the powertrain system itself, or it cannot be attributed to the chassis system or the body in white or the vehicle wheel. It's only a property that emerges from the interaction of all those subsystems. And the velocity is fairly straightforward to understand. However, if you look at the EMC and electromagnetic compatibility, it might be more difficult to set the proper KPIs and know what you need to measure within the system to properly verify your system. And so when I started my PhD 2 years ago, I wanted to first understand who were the main stakeholders involved in sort of going from MBSE systems engineering to simulation, and then some testing and verification. And I've tried to impersonate them, so I've given them names on this slide. And we get Fred, Tom, and Mary, three different stakeholders, 3 different engineers in the team, and they all want to realize a successful system. And they all perform different activities, right? So you've got Fred, who is defining requirements, defining acceptance criteria for the requirements, and I'll explain later why I have KPIs in the bracket. And then he establishes traceability between the requirements and the scenarios. You got another guy called Tom. He reads a system description produced by Fred, who might be a systems engineer, Tom being a simulation and model engineer. creates and manages a model and sets up the model interfaces so they are interoperable and they are reusable. So that's his responsibilities. And last but not least, we've got Mary, who drives test cases based on some of the scenarios described by Fred. And she runs the simulations, runs the tests, and reports the results. And in an ideal world, they all work together. They all share the same vision. They share the same glossary of terms. However, what we've seen is their operations could often be very siloed. And so, as a starting point, for me, it was important to understand what was really needed from my work. So, doing a bit of systems engineering and trying to systems engineer my PhD as I went through. And so what really was needed was to improve the artifact exchange, right? So why would Tom need to start reinventing something from scratch if Fred has already done the work in the previous lifecycle stage? Eliminate ambiguity, so make sure they're all on the same terms, make sure they understand the terms in the same way, they don't have different definitions or different definitions for the same terms. And look at whether what we do could be executable and quantitative. So if we build a model, what engineers like to do is then press a button and simulate a model. Well, that's not necessarily what you do in systems engineering and model-based systems engineering, and running simulation is a bit more difficult. So there was a driver for having these artifacts executable and quantitative. And see if we could explicitly define the temporal properties of our acceptance criteria. So when do we have to measure that? When does the property must hold true? And so essentially looking at how we could then use all the artifacts to facilitate system analysis. And I'll just try and quickly explain this slide as I go through. And so what we found out when I worked with the stakeholders, that what they actually understood by KPIs in most cases, they were acceptance criteria. And so I was thinking, yeah, well, that's great, because these acceptance criteria are attributes of requirements. And it was good seeing them that they appreciated that the requirement isn't just a requirement statement. There are attributes associated with the requirement, and the requirement statement is essentially just the tip of the iceberg that you can often see. And these requirements were traced to scenarios, and scenarios together with environment, and some models come to essentially create a functional test. And on the other side, from what the Mary and Tom would be interested in, well, we've got acceptance criteria, which really assess results of some simulation, and these results quantify functional properties of models, and these models are abstractions of system elements, and they really are part of the functional tests that we run. And it's all used to analyze the behavior of the system of interest. So having this conceptual model, as I call it, really helped me to understand what the different actors understood by the different terms, and helped me to sort of bring everyone on the same page, so that when they were using the different terms, they knew what the other people, what the others meant. And so the two things really here, while we needed to be able to have a quantitative value, so make sure that the acceptance criteria are quantitative, and we can measure them, essentially put a real number to it, and then having the traceability, so that we can essentially trace through sort of like top down and bottom up. And so just on the importance and how we went about making sure that these are quantifiable. So there's actually a lot we can learn from computer science, and computer science that essentially people in computer science do what's called a formal verification. And in formal verification, you can specify a property for your system, and then use methods like theorem proving or model checking to make sure that that property always holds, right? So if there's a trajectory in your system that would violate the property, this formal verification method would find that. And for that, they use formal specification languages. And one of there's many different FSLs, formal specification languages. However, the one of importance or interest here is one called linear temporal logic. Maybe some of you might be familiar with LTL, but this is essentially the syntax. So you have an LTL formula, which assigns consists of predicates, and then you have several like Boolean and temporal operators. So Boolean operators like negation, conjunction, disjunction, and or, and temporal operators such as always and eventually. So you can specify a property that must always hold true. So safety property eventually must be true, so something can be reached. And until property, so like a fairness property. And one of the challenges with LTL is that you can only get Boolean satisfaction output, so it either holds or doesn't hold. So we delved a little deeper into the world of formal specification languages, and as an extension to LTL, which was developed for cyber-physical systems, and that's signal temporal logic. And by signal, essentially, I mean, they mean time series data. So you can now specify properties for those time series data that you might get from your results of simulation. And so you can specify properties on continuous signals. You can define the temporal operators explicitly. So there are different variations of signal temporal logic. There's metric temporal logic, and some of them allow you to look at bounded and unbounded values. Specifying predicates using continuous variables, such as velocity or temperature, and you can get quantitative satisfaction output. So there's a qualitative semantics to signal temporal logic, and essentially what it allows you to do is use one of the property checkers I mentioned from computer science, an adaptation of those for cyber-physical systems, and you can compute the quantitative satisfaction of your STL formula. So here's the updated syntax for STL. So most of it is same as linear temporal logic. However, you now have timed always, timed eventually, and timed until. So you specify your start and end when this property must hold in your system specification. And just an example on the quantitative satisfaction. So for a requirement like this, we would have a requirement that the deviation from target speed shall be less than 1 kilometer per hour. We've got two traces. You've got the black, which is the target velocity, and blue, which is the actual vehicle velocity. And the quantitative satisfaction essentially gives us the value of, it's called robustness, STL robustness in here, and essentially it tells us whether the property holds or it doesn't hold. So on the first graph here, we get our actual velocity outside of the 1 kilometer per hour boundary, and therefore the property doesn't hold, and we can compute how badly the system failed that specification. Second graph is positive, so property holds, and this is how well our system performed. And the last one is the worst case of these three. So we were far out from the 1 kilometer per hour boundary, and our property doesn't hold, and we can put a real valued quantitative number to the result. And STL is very expressive, and not too difficult to learn. So it's just a few examples on what you can do with signal temporal logic. You can specify properties for maintaining a safe distance. So this essentially specifies a property that must hold true, and it says that the distance of the ego vehicle to the preceding vehicle. So in your adaptive cruise controller, right? So you have a ego vehicle, the one you sit in, and then you have a vehicle in front, and you want to maintain a certain distance. So this is really specifying that it must be always some minimum distance, and the whole property is a function of the velocity of the ego vehicle and the reaction time takes for the system to react to any changes of in the velocity. And it must always be greater than 0, because 0 would mean that you've run into the vehicle. Specifying properties for acceleration and comfort. So the driver comfort, looking at the longitudinal frequency analysis of the longitudinal acceleration of your vehicle, and specifying that it must be within certain boundaries. Any response to cut-in events. So saying that if a vehicle cuts in, and you must decelerate, so your vehicle must essentially reduce the velocity and slow down. Or any overtaking maneuver. So if overtake is to occur, then the distance to the vehicle in the adjacent lane must be greater than a minimum distance that you define. So very expressive, not too difficult to learn and pick up. Very good structure. And the next challenge was on how we can make these STL specifications of traceable, and how we can establish the traceability between all the artifacts that we have in our process. And so it was really good to see that there was already an MBSE practice in the company, in AVL, and I was fairly new to systems engineering and MBSE, so at that point I formed model systems engineering was purely just simulating models, and it turned out it's not really that. But what they were doing was essentially building system models at a fairly low level, so they would be modeling the control modules and looking at the exchange of the CAN messages between the control modules just to understand the complexity and be able to explain that to the customer. So I thought, well, let's do it at a slightly higher abstraction level, and try and capture some of the information you would be exchanging in PowerPoint slides, like the slide we saw previously on the free lane constant speed velocity, and try to codify that information, try to explain that in the model. So let's try and we suggest this sort of like model. There's many different MBSE methods you might be aware of, and there's a lot you can model. However, if there's no downstream process that would use the information, there's no point in modeling that. So the simplest method we proposed was, well, just capture the scenarios, model the use cases for your system, trace them through requirements, and then essentially write down the system functions that would be realizing the use cases, capture the operating modes, the system states, the different system states the system would go through as it accelerates, decelerates, and travels at a constant velocity, and then try and establish the allocation, essentially the allocation between the system functions and the component elements. So this was really to give us something to work with, to be able to trace the predicates of the signal temporal logic specifications onto the interfaces of the functional interfaces in the system itself. And so as an output of that process, we get the structural and behavioral information, and we can now establish traceability from the requirement. We already got requirements of scenarios, but now this is requirements of system states. So you can have some properties that must always be true within a certain system state, such as accelerating or creeping or decelerating or downshifting, upshifting. And we can link the predicates directly to the system interfaces. One of the challenges was trying to capture STL in SysML, and there's ways you can model constraints, and there are constraints languages you can use from UML to capture constraints in your system within SysML. However, we'll just keep it simple, and so we just defined several constraints blocks for these temporal and Boolean operators in SysML, and these can then just be used in constraints diagrams to define the properties of your system. So we have the implication, timed until, or not timed eventually, and timed always, and they would have constraint properties such as the proposition A must hold true until proposition B happens, and the proposition B must happen within a certain start and end period. Timed eventually, again, property A must hold true within A and B, a start and end, or end essentially linking to two properties if you need to. So fairly simple construct. It was easy to understand by the engineers, and why add more complexity to the system if you don't need to? And the specifications can be reusable, right? So you could have electric vehicles, you could have hybrid electric vehicles, you could have conventional ICE powertrain, and if there's an ADAS, it is an adaptive cruise controller, it will always have certain properties that have to hold true in that scenario, so you can reuse them between different projects. You don't have to always try and specify them from scratch. And so let's look at the case study here. So we have the original piece of information we were given, which is a PowerPoint slide on the adaptive cruise controller, showing a 3-lane context. So no other vehicles on the lane, just one single eco vehicle on a motorway or free road, and traveling at constant speed. So the driver sets a velocity for the cruise controller, and the cruise controller just tries to maintain the velocity. And we can model that or codify that in SysML, and we essentially just say, well, there's a context with some scenario. We call it front 3-lane constant speed, and there are several actors within that context. So we have the driver sat in the vehicle, specifying the set point velocity. We have the vehicle trying to travel at a certain velocity, and then environment that essentially tries to disturb the system a little bit. And with a context like that, we can specify the interaction between the different actors, so looking at the functional and structural decomposition. And so we can see we have the driver has got his brake pedal and accelerator pedal, so he sends brake pedal command and accelerator pedal command to the vehicle, and he can send the set point velocity to the vehicle as well. The vehicle then feeds back the actual velocity, which is displayed on a speedometer, so it's a piece of information that the driver can see. And there's a bit of an energy exchange as well. So for the actual acceleration, as the driver, as the vehicle accelerates or decelerates, the driver is either pushed back into the seat or leans forward. And the environment really just creating some resistance for the vehicle traveling on the free lane, in a free lane context. And so this really allows us to look at the interaction between the different actors and make sure that we have captured everything we need for our system to do and how it should do. And so maybe the acceleration, again, this is an emergent property, right? So because the driver is pushed back into the seat from the behavior of the vehicle as a system. And so if you just think, well, as a vehicle traveling on a free lane at a constant velocity, you might miss out on some of the interactions with the driver if you don't map that, if you don't do some modeling. And we can easily model all the target sets, all the KPIs that we had on the previous slide. So we have the max delta to target speeds, which essentially traces to an absolute delta to set point velocity, which is a function of the set point velocity from the driver and the actual velocity from the vehicle. And we have a target value, which is a power property called max desired velocity delta, similar for the mean absolute delta set point. And then we have a property specified for the AX, the longitudinal acceleration disturbance. And so the next big challenge was to try and press the simulation button, press the run button, which just wasn't there, unfortunately. So it might have seemed that some of the modeling effort was just pointless and there was no use for it. But just try and get a PhD student to try and come up with some smart ways, they said. So we tried and did. So what we were able to work with was the system model, and we had developed the acceptance criteria in the system model, captured some of the constraints on the properties that must hold true for our scenario, and established the traceability to the requirements and the model elements. So this is already there in place, which is great. And they say that behind SysML is a model. So the main promise of MBSE, model-based systems engineering, is that you are creating a repository or of some sort, or model database of information that you can query and extract information from. And it turns out it's a bit more challenging than that. However, there is a OMG standardized model exchange interface called the XMI model. And so we adopted that and exported our system model into this OMG standardized XMI format, and then just used a bit of custom scripting in Python to extract the information that we needed. So in this case, it was extracting the predicates for our STL specifications that are traced to the system elements and the functional interfaces, extract the targets that we needed and the traceability to both the scenario and the context. And then through just simple string manipulation, we were able to automatically construct the STL formulas. And so this really gives us, just trying to figure out how this works, the traceable STL specification. So we now have an executed machine-readable and a human-readable specification. So one of the benefits of that is that if you export the STL formula, if you create STL formula, it's not a bytes code or binary code that you wouldn't be able to audit. So if you need to audit that, it's still human-readable. And it's executable, right? So one of the main benefits of that is that you can automatically export something that can be executed, and so you are removing the potential step where a test engineer would come down and look at the requirements and look at what the described acceptance criteria were, and would have to write down the piece of code or the conditions in your software that would analyze the results of your functional test. So now we have an executable, automatically exported mathematical expression that can be used to evaluate the output of your simulation or test. And the next is the sort of model transformation from the system model into something we can actually simulate. So if you go around the tool windows here, they will say you can run simulations in their tools and simulate SysML. However, what we wanted a more standardized, less vendor lock-in approach. So again, exporting the information, the structural information from the SysML tool into and the OMG standardized XMI model. And we thought, well, instead of building the models that, again, or so building the simulation models, we can just reuse the artifacts that people like Tom, the simulation engineer, would develop, and they would have maybe a library or essentially develop some simulation models in Python, Simulink, MATLAB, whatever simulation environment you can think of, and let's try and link them together. And so there's a functional mockup interface standard, which allows you to define functional mockup units. And this functional mockup unit is essentially a black box version of your simulation model. So if you have a model in some simulation environments and you have some IP, some proprietary information captured in there, like control logic, for example, you can encapsulate that in this FMU black box. And you can connect those FMUs using this SSP standard. So SSP stands for System Structure and Parameterization. And what this allows you to do is interlink the different FMUs into a co-simulation model. So co stands for coupled simulation. And you can then use tools to run that co-simulation. So the tool we use here is an AVL tool called Model Connect. And we can, it's got a button, so we can press the button and run the simulation, which is great, what we would expect. And we get the output, so we get some data showing us what the target velocity was and what the actual velocity was of the vehicle. So just a quick overview of the few steps we just went through. So we went from the SysML constraints, capturing the acceptance criteria, capturing the KPIs, depending on how people understood it in the different stages of the life cycle, to the signal topology specification. So just extracting the predicates, extracting the temporal and Boolean operators, and doing some string manipulation to be able to construct the STL formula. Going from the SysML internal block diagram from the IBD into the SSP structure. So that's really capturing the interaction between the different drivers, between the different models, if you like, here in your big co-simulation model. Set the scenario conditions. Set the target velocity, what the target velocity needed to be, run the simulation, and we can automatically evaluate the STL satisfaction. So here is one of the good things about simulation. You can try and exploit some of the failure modes of your system. So here we deliberately applied some step input, some step disturbance to the system, to the control for the cruise controller to show a possible violation. And the what's shown on this slide, on this graph here, is both the violation intervals, so when the property doesn't hold true, so when the property is violated, and also how badly your system failed that property, the specification. So you can no longer just say, well, it's pass or fail, but you can put a real valued number to the output. And you can also look at what happened, why did it happen, and when it happened during the simulation run. And again, this is sort of like just running the simulation and running the automated STL property checker as well. So no need for humans to write down the acceptance criteria and look at the data and try and understand whether it passed or failed. And so, just quickly look at some of the potential use cases if you do this at a bigger scale. What could be done just beyond running a single simulation, evaluating a single scenario, a single specification. So one is on identifying the root cause of a failure. So if you have at a system level, your actual velocity isn't what the target velocity was specified. You can look at the one level down if you have that information modeled in a cost simulation model and in a system model, and you can maybe look at the drive torque, and maybe that's not sufficient, so fail the property there, and maybe that you can link that down to the motor torque. So if you have the traceability from the system down to the subsystem to the components, you can really identify what was the root cause of the failure. And so really going up is what failed, and looking down is why that failure possibly occurred. And it's not as straightforward as that, so there could be many different contributors to that failure at a high level. So it's important to have the traceability within the system model to be able to identify what properties hold true during the simulation, during the test, and which property didn't hold true. So why the system didn't behave as it should have. And as we get the quantitative, the real valued outcome of the STL satisfaction, we can identify the risk severity and then do some analysis and say, well, maybe to fix this failure costs us millions and millions of pounds or euros. However, if it just causes a nuisance to the customer, might be willing to accept that. We don't want to spend the extra money on fixing the failure. So this is a really, really important one for my sponsoring company to understand the severity of the risk of this failure occurring. And so just to conclude, so what we really achieved was to set out the methods, which allows you to clearly define what needs to be measured and what interfaces, also system elements, this traces to. Improve the traceability. So, as I said, one of the benefits of MBSE is that you get a repository or model of sorts where you can which you can query, and it's easier to do in PowerPoint and Excel spreadsheets and Microsoft Word documents, and it's a method that sort of facilitates the system analysis as you do that. However, there's no such thing as free lunch, so it introduces potentially high upfront cost. So it goes in a slightly different direction because we've seen, well, most of the talks on simulation conferences and other conferences is on how can we increase that, how can we shorten the development cycle even more. Well, I'm saying, well, you need to spend a little bit more time working with your requirements, because at the end of the day, that's what you need to verify, and that's what you are contractually agreed to in most cases. And so you need to write down, as you're writing down the requirements, you need to write down the acceptance criteria. You need to make sure that they are quantitative, they are quantifiable. You know what you need to measure. You know how to measure that as well, so that if you write down a requirement acceptance criteria, somebody else won't say, well, it's not really good, I won't measure that way. I'll just do something slightly different. So we are making the people spend a little bit more time in the initial development, the earlier life cycle stages to really put more formalism and rigor into the process. And the benefit is there, just further down the line. Higher modeling effort, so we require the system modelers to capture those scenarios in system model and look at the interactions between the different actors. So there's an extra modeling step involved in the process. And as I said, if you look at the system level, subsystem level, and you make sure you get a traceability between them, the complexity grows with scale. So you have to really have a good training and a good application of MBSE to be able to manage that complexity and make sure you're not adding any, not introducing any additional complexity into the system. And so this is everything from me. I'd like to thank you for listening to my presentation, and I'll welcome any thoughts or questions you might have.
Thank you, Lukas. I'm going to start with one from Slido. I've got a question from Slido just saying, writing STL specs correctly and comprehensively can be challenging, especially for intricate systems. How did you manage that complexity, and did computational intensity matter?
So the computational intensity, I'll start with that, which is a very interesting question, because to be able to evaluate the temporal properties, you have to do dynamic programming to look at recursively at the value you've just computed the step before, and make sure that within a specified time period it holds true. So there's a bit of compute required. We haven't put a quantitative number to the amount of compute required to be able to compute that specification for like the temporal, the timed always or until. But it's a really good consideration, a very good question, and it can be challenging writing those STL specifications. However, we broke it down into essentially just specifying the predicates. So saying that a velocity must be less than or greater than a certain target value, or a temperature of a system must be less than or greater than a certain target value, and then just linking those predicates to the system interfaces. And then the and having the traceability to the Boolean operators, which essentially links to the scenarios model in a system model. So the engineer really needs to specify the predicates and link those to the interfaces, and then the SDL is constructed in the sort of like the script. So after the model is exported into the standardized OMG interface, we can just do some string manipulation and construct the STL formulas automatically. So that's slightly essentially that complexity is taken away from the system, and it's taken care of after you've linked your predicates.
Bruce Elliott, University of Birmingham. Thank you. I like what you're doing, and I'm wondering whether there are more benefits that you could go into your business case that I didn't see, or perhaps I missed them. Do you get reuse benefits in the long term from making it quicker to test new models, in the medium term by making it quicker to test upgrades to existing models, and in the very short term for regression testing when you're in a cycle of fixing bugs and retesting?
Yeah, absolutely. So this is really the next paper I'm hoping to publish as part of my PhD. And the main, the overarching goal of my PhD is to look at how we could automate verification validation. And we try to learn a lot from the computer science guys, because they're quite smart guys, and I think that's something we can transfer over to cyber-physical systems. And so I'm looking at a method called falsification, where essentially I was taught to do verification. I said, well, I won't do verification, I will do falsification. So I will flip it upside down and say, well, I want to, because verification is essentially proving that a certain property is true in your system. Or from the computer science perspective, or you build the right system, or the system right, as defined in the handbook. However, with falsification, you want to go and explicitly search for any violations to your properties, right? So really, this is using optimization, where this STR satisfaction is used as an objective value in that optimization approach. And what you're trying to do is you're trying to find a trajectory of your system or execution of your system that would try and drive the system down to failure. So if the STR satisfaction is 0 or below 0, it means you violated your property, you failed your requirement hasn't been met. And so with optimization and using the STR satisfaction as an objective value, you can search for any violations of the properties that you define. So this is I guess the business case for using having this traceability and doing all the upfront work. And one of the challenges with optimization is you can generate many different you can use different optimization approaches and methods, and some of them tend to be quite exhaustive. So you do generate a lot of simulation runs, you do generate a lot of execution runs, and you have a lot of data and a lot of potential use cases or test cases. So what I actually try and look at is to try and cluster the test cases based on the STR satisfactions of the different properties. And for your regression tests, essentially just find the most dominant test cases from the different clusters that you have to run. So you don't have to rerun hundreds of thousands of test cases in your system if you release an update. You just need to rerun those that would most definitely show you the violation of your property.
Hi, Jake Lynch, Product Line Specialist, Technical Manager in Systems Engineering at Bentley Motors. So just looking at your example in terms of the cruise control, and it might link on to that question that you've just answered. For example, so obviously with your test cases, you'll be testing for different scenarios that cruise control will be put under, but in a specific example of, for example, rapid surface or gradient change, taking the surface, for example, say you were going from tarmac to grass. Yep. Obviously, there's an infinite amount of coefficient of frictions that would change on that transition point. So how would the simulation deal with that, and could you be confident that it would give a successful test? Absolutely. So that's a great question, and one of the benefits of using the domain-specific toolchains is that you can use the tools that are best fit for the purpose for the test you want to run. So I wouldn't be trying to model the coefficients of friction and the interaction of the vehicle with the tires.
and the tire, trying to capture the tire dynamics in sort of like from first principles, that would be fairly challenging. But you can use tools like CarMaker or other sort of more specific tools for vehicle dynamics, and so you can essentially just use what's best for the tool for the test case you need to run. So this is really what the simulation engineer would deem appropriate, and then through the cost simulation model, you can link those different cost simulation models together and run one big cost simulation, essentially just using the specific tool chain for what they need to be, for what they're good for, really. So whether it's CarMaker for your vehicle dynamics and interaction with the tarmac, or if it's simulating for your control logic, so you can just use what's best fit for the purpose. Yeah, really good question.
Okay, I'm afraid we're going to have to cut it there. There's obviously a lot of engagement, so Lukas, I hope you're up for many more people coming to find you during the breaks.
Absolutely. Yes, just reach out to me on LinkedIn as well.
So thank you very much, and once again, please put your hands together for Lukas.